In this video, we're going to give a high-level overview of a computer system. So a computer technically is, well, a collection of hardware and software working together to accomplish a task. Yeah, that's technically correct, right? But that is not very useful for us engineers. A computer is a complicated device, and so we're going to actually start at a high level and work our way down, like an onion, peeling back the layers. So you can think, actually, a computer is a state machine, or I've got state machine listed here. It's a finite state machine. And so let's remember what a state machine is. First of all, we know that we can easily build a state machine, right? But the circles there are states, right? And a state is like the behavior of our circuit. We can actually design circuits that change slightly their behavior depending on which state the circuit is in. The arrows in a state diagram, or this state machine, represent transitions from one state to another state. What makes a circuit transition to a new state is the inputs, or input singular, maybe several inputs. But those inputs are determining which state we will go to next. And also when we transition, and I haven't shown it here on the state diagram, our outputs, or maybe one output or several outputs. So each time we transition to a new state, we can possibly have an output. And so you'll see here in my state diagram that I've drawn, it's got, you can see at the bottom, 3 separate paths. Each path here is accomplishing a different task of operation. And this specific structure isn't important, it's just an example, but you'll notice the different paths, and each path leads back to the start. So that ends up being a little important. That's not true for all finite state machines, just here, but we want our state machine to keep looping back to the start after one of those paths. Okay, and so again, we know how to build this thing. It's a state table. We go from the state diagram to the state table, and then we go to the K-maps and we synthesize the next state logic and the output logic, and then we can build that with flip-flops and logic gates. All right, so on my example here, we might call this path, the leftmost path, operation 1, and we might call the middle path operation 2, and we might call the path on the right operation 3. Now again, I want to emphasize that at this moment, the number of operations or paths and the number of states, you'll see that the leftmost path has one more state, required by each operation is unimportant and arbitrary. I had to draw something, and this is what I drew just as an example. But the important part is that each path leads back to the start, and that there are multiple paths. Now, finite state machines take inputs, as we know. Maybe one of those inputs will signify which of these paths to take. Let's call that, I don't know, the operation code, right? Or opcode for short. Okay, so you can imagine a cycle, and all of these paths are going back to the start, and the opcode is determining which path that we're going to take, but we're eventually just going to get back to the start. So we've got this cycle going on over time, right? Maybe that takes some time. And then maybe there are different operation codes at many different times. And so we might start to think about like sequencing those operations. Sequencing those opcodes like I have listed here on the right. Now, we might put these opcodes in some sort of storage device, some memory, so that the sequence is maintained, again, like I've shown here. Now, this, again, is just arbitrary, and it's just for example. So maybe the first time we cycle through the state machine, we go on the leftmost path, opcode 1, and then maybe when we cycle again, we go on the leftmost path again, opcode 1 and opcode 1, maybe opcode 2. Again, that's just for example. And now you can imagine then that we would have like some more hardware or another state, right, that fetches the opcode. Suppose that is done at a state just after the start, before the state machine branched out into paths. So in this picture I have here, the upper arrow of this circle is like getting it from the start, and the lower arrow of the circle is where the branching out would happen. So in this case, the state reads in opcode 1 in this example, and then proceeds to execute operation 1, or go down the leftmost path. Then the state machine cycles back around. It fetches opcode 1 in this case again, and maybe it fetches opcode 1 again until all the opcodes have been fetched in sequence and their corresponding operations executed. Now, the opcode is simply a string of ones and zeros. That's all our computer is allowed to understand, right? Being that we implement the machine with logic gates and transistors and switches and all that binary stuff that I don't want to review here. The sequence of ones and zeros is called an instruction. These sequences can be anything. I had to pick something just for the sake of this example, so these are the strings of ones and zeros that I chose. The exact string in this example is not important, but what is important, though, is that each opcode is unique, and each opcode does not change. So you'll see that opcode 1 at the top is 100100 something, and then the next opcode, which also is opcode 1, is 100100 something. So the opcode cannot change. Opcode 1 is opcode 1. But then opcode 2 has to be unique, so it has to be different from opcode 1. The instruction set is a set of the instructions that the state machine is capable of performing. So the instruction set is this collection of instructions. In this example with 3 paths, the instruction set has a length of 3 different paths, 3 instructions comprising the instruction set. You can imagine that each opcode is fetched in sequence and the corresponding operation is executed. But you can also imagine possibly skipping opcodes in the sequence based on like certain parameters or like what we've already like witnessed somewhere. And you can think about like an if statement, right? How an if statement would work. You can also imagine like moving back up to a subsequence of opcodes already seen by the state machine. And again, you can imagine like a loop doing that. And so this flow of opcodes that are read by the state machine is the program or software, and that is developed by the programmer. Nice, right? So you can see how like the computer is, at least at a high level, coming together here. Now, that was the software, the sequence of opcodes, and how we execute them. The hardware, on the other hand, as we said, is the state machines. It's comprised of flip-flops and logic gates. But we also need memory to store the instructions, right? The opcodes. The memory is comprised of more logic gates, memory cells like capacitors, and possibly other analog circuitry. There are actually many different types of memory, and some use capacitors, some use some other things, and I don't really want to get into that right now, okay, which is why I'm being vague here. But we're going to move on. We will also need some other hardware in our computer, like we might need an adder to perform bitwise arithmetic or strings of arithmetic on strings, right, of bits. We might need fast storage or more memory, and we will definitely want input-output or I/O circuitry. So you can see how all of these things start working together to form the computer. And I want to point out that these things do not change. At least you cannot change them easily, certainly. The hardware is the hardware, period, full stop. It does not do anything useful until the software instructs it to do something. All right, so this was a high-level overview of a computer system. Next time, we're going to look closer at the hardware, and next time, the software. Thank you.